April 1815, Mount Tambora erupted, launching gas, rocks, and ash miles into the sky. The eruption destroyed the town of Tambora and created multiple tsunamis whose combined destruction killed over 70,000 people. But the damage did not end there. The eruption launched sulfur dioxide into the stratosphere, where it reacted with water vapor to produce sulfate aerosols. These molecules were too high for rain to wash them back to Earth, so they stayed, trapping and reflecting the sun's light before it could reach the surface of Earth. The following year, across Europe and North America, this layer blocked the sun's rays and produced the year without summer. Snow fell in June across New England. Summer frost covered the eastern US all the way to Virginia. In Europe, the skies were cloud-covered and poured rain, leading to disease, crop failure, and famine. Communities collapsed. Refugees fled their homes, searching for food and safety. It was decades before the scientific community identified the culprit and measured the impact. The Tambora eruption and subsequent sulfate aerosols caused the global average temperature to drop by more than 2 degrees Fahrenheit. Luckily, sulfate aerosols settled out of the atmosphere after a few years, and Earth's climate returned to normal. The introduction of these sulfate aerosols blocked the sun's rays and caused the planet's temperature to drop. Let's compare this with climate change, global warming, and the introduction of carbon dioxide into our atmosphere. Climate change is caused by greenhouse gases. These gases allow high energy rays from the sun to pass through them. But after that light hits the Earth, some is reflected back towards space as infrared radiation, or heat. These gases can absorb and reflect that heat, keeping it within our atmosphere and close to the Earth's surface. If we didn't have these gases, Earth would be a frozen wasteland, likely devoid of all life. But there can be too much of a good thing. The principal greenhouse gases are carbon dioxide, methane, water vapor, nitrous oxide, and CFCs. Each of these molecules have different properties, such as how long they last in the atmosphere and how much heat they can trap and reflect. CO2 has a global warming potential, GWP, of 1. CFCs have the highest, followed by nitrous oxide and then methane. Since water is constantly condensing and falling as precipitation, it does not contribute to climate change. So if CO2 is a weaker greenhouse gas, why do we always hear about it? CO2 is by far the most abundant greenhouse gas in the atmosphere, so it has an outsized impact. In addition, CO2 can remain in the atmosphere for 300 to 1,000 years. Methane is the next most critical gas because its GWP is more than 80 times higher than CO2, and we are quickly releasing more due to fracking for natural gas, another name for methane. But methane only remains in the atmosphere for roughly 9 years, long enough to do damage, but not nearly as long as CO2. Humans have released more than 1,480 gigatons of carbon into the atmosphere. In the carbon cycle, CO2 is regulated by plants and animals sequestering the carbon in their bodies and being buried underground. We are digging up that fossilized carbon and using it in the form of coal, oil, and natural gas. We are putting our finger on the scale and disrupting a system that has self-corrected for millions of years. Major disruptions from Earth's past, such as global volcanic activity and asteroids, led to catastrophic die-off and gradual recovery. We have become the major disruption. We have successfully altered the climate and increased Earth's global temperature by 1 degree Celsius, nearly 2 degrees Fahrenheit. We are already seeing the effects: wildfires, drought, severe storms, heat waves, floods, and glacial melt. These changes are already affecting people's lives and influencing population movement. What we have to ask now is how bad will we let it become? A 1.5 degree Celsius increase is nearly inevitable, but will we hold it there or let it increase to 2, 3, even 5 degrees? It all depends on us. How much more carbon will we release? In a future lesson, we will consider the complexities of sea level rise, ocean acidification, and changes in weather patterns. At this point, you know how we got to now. The only question is, what are you going to do about it?